Good morning guys, and welcome to today's worked exam answer video. Today I'm having a look at another rate equations question, but this time the focus is on the Arrhenius equation, and this is a particularly tricky Arrhenius equation question, a little bit of a tongue twister there, because we're being asked to calculate the temperature, but we cannot calculate the temperature using this format for the Arrhenius equation, because as it appears here, the temperature is part of the fraction that is up to the power of this E, this mathematical constant. So we're going to need the other version of the Arrhenius equation, and this was the first time, this is from the 2023 paper, this was the first time that AQA didn't give you the right format of the Arrhenius equation that you needed. Now, you can just rote learn both formats. If you are not happy sort of working from this one to the other one, I'll explain how we go from here to the other one, but you can just rote learn that as well. And then when we have it in the other format, we can rearrange it to get T equals, which still isn't actually very nice of a rearrangement. Then we can sub the numbers in and then we can get temperature. So we're told that for any chemical reaction, the relationship between the rate constant and temperature is shown by the Arrhenius equation. And we're focusing on the decomposition of gaseous, ethanoic and hydride. And we're given, as I said, values for the activation energy, the Arrhenius constant, the rate constant, and then we're given the gas constant. And we've got to rearrange the Arrhenius equation, put those numbers in to get a value for temperature. Now, the first thing that I'm actually going to do here is have a look at the units for these values. K and A's units will always be the same as each other, because in this format of the Arrhenius equation, the units for activation energy, gas constant and temperature will all cancel out. So therefore, whatever the units for the rate constant are, A has to match. We're never going to have to change those. We know that K's units can be variable, but we would never be changing those in an Arrhenius type of question. Temperature will always be in Kelvin, and if you're given a temperature and you're working something else out, they may give you it in degrees. Activation energy needs to be in joules per mole, and we're so used to seeing kilojoules per mole for things like enthalpy changes that you might look at that and think, oh yeah, that's right. For the Arrhenius equation calculations, activation energy has to be in joules per mole. So the first thing that I'm actually going to do is convert that to give me 34,500 joules per mole. And if you're ever unsure, again, we can look at other units to give us a bit of a helping hand. So the reason why activation energy, gas constant and temperature units all cancel in this fraction is because we've got joules per mole on the top for the activation energy, then the gas constant has joules per mole in it as well, so they would cancel from the top and the bottom, and then we've got Kelvin to the -1 and temperature units would be Kelvin, so they're going to cancel as well. So because the gas constant is joules per mole, the activation energy also needs to be in joules per mole. Okay, now in terms of how we're going to change the format of this Arrhenius equation, we can't work out a value for the activation energy or temperature if you ever get given an activation energy question using this format, because they're both up in that power. So we need to get rid of the E function, because that will bring what is currently up in the power out of the power into the main part of the equation. Now, E is a mathematical constant, it's a button on your calculator, and what you will hopefully see is that for me certainly, the E function is the same button as the LN button. The E, you have to press the shift and then the LN button to get the E, but they're on the same button because they are mathematical opposites of each other. Just like adding and subtracting are opposites, and multiplication and division are opposites as well. So in order to get rid of the E, we need to take the ln of everything. So that's the first thing that I'm going to do, and I'm going to get ln of the rate constant K is equal to the ln of the Arrhenius constant A, and then we're going to add to that, because we've got these timesing together. There's a log rule called the product rule, and if there's two things times together, you take the ln of each and add them together, and then that becomes the ln of E to the minus EA over RT. Now, because the ln and the E are opposites of each other, they will cancel each other out, and then you can't have the minus EA over RT as a power when you've cancelled these two things out, because what is there that would need to be to that power? Not sure that made sense as a sentence, but I also know that it doesn't make sense to have that up there when there's nothing here. So we can bring that down into the main body of the equation. So we've got ln K equals the ln of A, and then we've got plus minus EA over RT. Plus minus gives us a minus, so minus EA over RT. And that is the second version of the Arrhenius equation that you can just rote learn. You don't need to show how we go from this version to this version. You just need to know both versions exist. And I guess what you can calculate from each version. This one, the only thing we could work out would be K, if we're not given the rate constant value, or A, because of that all being up to the power. From this version, we can work out the activation energy, the temperature, as well as the values for A and K. And this is the version that we use in the graphical questions as well, where we plot a graph y equals mx plus c. We plot ln k on the y-axis, 1 over t on the x-axis. This would be the y-axis intercept, and then the gradient is minus EA over r. And again, that's a way we can work out activation energy. Anyway, to continue this question, we're looking for temperature. So the first thing that I would do, because I don't like having negatives, is I would put the EA over RT over onto the other side to get rid of it being a minus, and then I'm going to take my ln K over so that I've got the EA over RT on its own on that left hand side. So EA over RT is equal to ln A take away ln K. And this is where the rearrangement gets a bit messy, because I'm then going to need to take the R and the T over here, and I'm going to have to times the ln A and the ln K by the RT, and that would be how you would rearrange this to get the activation energy, if that's what we were being asked to do. But we're not, we want to get temperature. So now that the temperature is not on the bottom of a fraction, we can now take the ln A minus ln K times R and put that underneath the activation energy. So activation energy divided by ln A minus ln K times R, all of that is then equal to temperature. Quite a lot of work there in rearranging that equation. It's not very nice at all. But once you've got to this point, it becomes an easier question, because we've got the activation energy and we've converted its units already. To get the ln of A, you're just going to press the ln button on your calculator, and then 1 times 10 to the 12. Take away ln, press the button on your calculator, 2.48 times 10 to the 8, and then times that by the gas constant, 8.31, and then 34,500 divided by all of that will give us our temperature. And when I did that, I got a value for the temperature of 500. It's 500.07. I'm looking at the significant figures in the question, and whenever you're quoting your answer, it should always match the lowest number of significant figures in the question. If they're all the same, obviously go with that. If you have different numbers of significant figures, then it's the lowest number that have been used in the question. So we've got 3 significant figures there, we've got 3 significant figures there, 3 there and 3 there. So I'm going to need to give it to 3 significant figures, so not 500.1, just 500. And that would be 3 significant figures. They don't always, in questions like this where they haven't specified about significant figures, expect you to give it to a matched number of significant figures. So I possibly could have also put 500.1 Kelvin here, and I'll write that there. I'm a bit I don't really like giving big whole numbers like 500 for 3 significant figures, because it's hard to tell if that actually is 3 significant figures, because we could have rounded up from sort of like 450 point something all the way up to 500. Hang on, is that right? Yeah, if we were thinking about sort of 1 significant figure, definitely, that's what I was meaning. So we could round up from 450.5 all the way up to 500 for 1 sig fig. So I don't really like giving 500 as an answer to 3 significant figures, even though in our case it would be. So I'm going to put my 500.1 there, and then I'm going to put my 500 to 3 significant figures there, like that. Apologies for that, managed to confuse myself there. But hopefully I've not confused you with the method, the rearranging, or anything like that. At this point, I've just subbed the numbers in, like I said, from the question and got my answer for 500 Kelvin. So the hardest part there was getting or regurgitating the other form of the Arrhenius equation and rearranging it. Subbing in the numbers was okay, so long as we knew to change activation energy into joules per mole. Thanks for watching, guys. Any comments, questions, as always, please put them either in the comments or drop me an email, missg.tutoringandresources@outlook.com. If anybody has any other Arrhenius questions they want me to have a look at, again, please let me know. And thanks again for watching, guys. Take care.